So good afternoon, ladies and gentlemen. I am very honored and happy to be here in this beautiful room with many physicists, but also many non-physicists yet, or just lovers of physics. And I am happy to describe you basically what is my dream, to be able one day to really cook the right recipe for a neutron star. And you will see how I intended to do this journey with my collaborators, both in experimental physics at LHC, but also with many people from theory, because we work hand in hand to basically realize this picture. What do you see in this picture? On the left-hand side, you see a typical collision at the largest hadron collider that we have in the world, the LHC in Geneva, that basically allow us to produce a lot of particles and also study their properties. And on the right-hand side, you see actually not only one neutron star, but two neutron stars, and actually the mergers event of two neutron stars, when they basically melt together and form something which we don't even know what it is, okay? And obviously this connection between left and right is not so easy, and this is what I try. So mostly working on these sides of the barricade, as you will see. But okay, so we start with the beginning, and we start with the mother of the neutron stars. So this is a simulation, a computer simulation carried out by a colleague of mine in Munich at the Max Planck Institute for Astroparticle Physics. This is a supernova explosion, okay? So it's an explosion of a star that might happen when stars are very massive. Very massive means at least 8 times more massive than the sun. Then when the mass is so large, the gravitational strength compresses the system and leads to an explosion, okay? And here you see this event that maybe you have heard about, that actually mankind even saw with a bare eye, right? And what is left after this explosion can be either a black hole or a neutron star. So this is where it all begins. So this is basically the birth of a neutron star. So, but clearly we want to know why these neutron stars are at all object of our interest. What is so exotic about neutron stars, right? And the thing about the neutron stars is that although the radius is very small, basically a neutron star is as big as Prague, right? With a 10, 15 kilometer radius. Maybe Prague is a bit bigger, but this order of magnitude, you know. The mass is between 1.5 and 2 solar masses, so twice as heavy as the sun. And you will see in a moment, in another transparency, what does mean actually in terms of density, okay, of this object. So, but clearly anybody can see that if so much mass is contained in so little volume, this system is extremely compact. Actually, to put it in a more convincing wording, those are the densest objects that we know exist, okay? And those objects, they are emitting, for example, radio frequencies, so they orbitate very quickly with periods of orbitations of milliseconds, and they can emit radio frequency. And that's why we know, for example, that they exist, because on Earth we can detect such radio frequencies. And this signal, as you will see also in a moment, allow us to determine the mass, to measure the mass, and to a certain extent also to measure the radius. So we really know they exist. We know their mass and the radius because astronomers measure this quantity. Not me, but colleagues from astronomy. So what is our job? So as nuclear physicists, we want to try to help astronomers to understand what is inside the neutron stars, because nobody knows what happened to matter when you compress it so much, when it is so compact, as it is the case of a neutron star. You don't know if you have new form of matter or you have the same matter that we know on this Earth. Indeed, we know that on the outer crust, you see here an artistic pie, piece of a cake, like, of the neutron stars. And we know that on the crust, we have ions, electron gas, neutrons, but we do not know what is inside the inner core. That's why you have here a lot of question marks. Maybe we have also only neutrons, just very close to each other. Maybe we have also some protons. Maybe we have particles that are very dear to my heart because I study them, hyperons, and you will learn what hyperons are today. Or maybe we even have just a quark soup. So not hadrons, where quarks are confined to triplets or pairs, but a soup where the quarks just interact with each other more freely. We do not know what is inside. And this is our job, try to cook a recipe. That's why the title of the talk is How to Cook Neutron Stars. Okay, so, but actually, it's very important for me that you have also, some imagination or some information about where these neutron stars are located, right? Whether they are close or far away from us. And here you can see that the nearest neutron stars is located at 200 light years, meaning that light takes 200 years to travel from there to there. So that's not so long, let's say, still a scala where measurements are possible, but if you compare it to the distance between the Earth and the Sun, which is only 150 millions of kilometers, and knowing by looking into Wikipedia that 1 light year corresponds to 9.5 billions, billions is 10 to the power of 12 kilometers, you see that basically the nearest neutron star is 10 million times more distance than the Sun from the Earth, okay? Another question that you might ask is how many neutron stars do we have? We know of about 2,000, give it or take, objects. Those are the numbers of the objects that we have observed in the last 30, 40 years. So not such small objects, not such a small number. Okay, so they are very far away. We have plenty of them, we have seen plenty of them, and we know they are dense, right? But I also want that you understand the maybe most spectacular measurement of the neutron star properties. That is the so-called Shapiro delay. So this measurement that I'm going to explain you in a schematic way allow us to measure the mass of neutron star very precisely. So we really know very precisely how heavy they are, right? And what is this Shapiro delay? You have to know that exactly like a very charismatic person always has at least one companion around, right? Same is for neutron stars. They very often come with a body, with a companion. This companion orbitates around, so the neutron stars, basically you have here 2 orbits. The so-called neutron star pulsar orbitates around the orbit, and the companion, which is typically a star which is called white dwarf, orbitates. So they do like a dance, okay, around each other. Okay, and I told you before that this neutron star can emit radio waves because it turns around itself. Think about the dynamo of your bike. When you switch it on and you bike, you produce electricity. In this case, the rotations, since you have many charges on the surface, induce radio waves. And you can see these radio waves, right? So this guy emits radio waves. You are maybe here on the Earth. These radio waves can be detected. Okay, what happens when light goes through a so-called gravitational field? Meaning, imagine that you are looking here, And basically, between you, observer, and the neutron stars, there is the white dwarf, which is kind of obscuring you, okay? Imagine that this rotation happens, and at some point, the white dwarf is really between you and the neutron star. What will happen to these radio waves? They will be deflected, because we know from general relativity that basically the things that you can see here in this animation will occur. On the left-hand side, you see how the radio wave go onto a straight path from the neutron star to the observer if they don't see any mass in between. But if you have a massive object that will exercise a gravitational field, what will happen is that light or radio waves, that's the same, get curved, right? And if the curvature occurs, what happens? Then the trajectory is longer. So the light will arrive to Earth, to the observer, with a delay. So what we can measure very precisely is this delay. And this delay allows you to know very precisely the mass of a companion, okay? Then, what do you need? If you have a system with two objects and you know the mass of one object, a very famous guy that you all know, Kepler, who was very long in Prague, actually, told us that by looking at the characteristic of the movement of two planets, if you know the mass of one, you also know the mass of a second. This is the way how the mass of a neutron star is determined, basically using the Shapiro delay and Kepler's third law. Okay, that's it. And this is actually a very smart combination of effects, because the result, which was first published for such heavy neutron star in 2010, is showed here in this mass distribution. So in physics, we like to have on the y-axis an observable. This is now the mass. And now, if a measurement would be perfect, you would have only a line. But the measurement is not perfect, so you have a width. The larger the width, the less precise is the measurement. But actually, if you look at the number, you see that for this particular case of a binary millisecond pulsar, which carry this name, which is basically a combination of one letter and several numbers, it has a code, this object, has a mass of two solar masses with plus minus, this is the uncertainty, right, of 2%. This is actually much better uncertainties than the uncertainty with which you can weight yourself, right? Because if you control your weight, you always have an uncertainty of normal 5%, because depending when you weight yourself, right, you are a little bit heavier or a little bit lighter. So this is an impressive precision. So summa summarum, what should you now bring home? Neutron star masses can be determined with very high precision, 2%. So, and astronomers hence can tell us very precisely. So if I want to plot a typical, let's say, collection of information of neutron stars, I will have a diagram where on the x-axis I have a radius, and we know that the range is between 10 and 15 kilometers, right? On the y-axis, I will have a mass, which goes from 1 solar masses up to 2 solar masses. And then what we have learned so far is that we can draw very thin lines, right? Horizontal lines. Why? Because we have this measurement, like Shapiro delay, which I just showed you, where we know very precisely the mass, but we have no idea about the radius, okay? So Shapiro delay measurement does not give us any information about the radius. Fortunately, although, there are other measurements that I don't have time to talk to you today, but you have to believe me that there are other measurements where mass and radius can be measured at the same time, at the cost of precision. Indeed, as you can see here in this example, this sketch, if you try to measure them at the same time, the precision that you achieve, it's at best 15%. actually, in the best measurement we have today of detectors placed on the International Space Station. So as you see that it is a diagram here which contains some information, but it's not, I mean, we don't have points, right? We have islands actually, just to show you a real plot, right? So this is one of the recent plot where you can see lines for Shapiro delay's measurement of masses around 2 solar masses, okay? But not only, here you have also measurement of neutron stars, which are actually much lighter. And then you see here these measurements comes from measurement of mass and radii, and this is the regime, or the range, which is covered by gravitational wave measurements, which are something we are not going to talk about today, but for sure you have heard about, because it was one of the recent Nobel Prize. So despite of the fact that these gravitational waves are very famous and known, I mean, this is the precision at the moment with which they can give us information about neutron stars. So it's not so much, okay? So you see, it's a very complicated business. Okay, let's continue. Now I want to let's say, make it clear how dense is a neutron star, what it means when we say dense, yeah? And in order to get a feeling for this number, we will just do a little mathematical exercise, a very simple one. We take the formula for the volume of a sphere. Knowing the radius, we can apply this formula, and we know the volume. And then we take the formula for the density, which is mass divided volume, okay? And then we compare the mass and the volume of 3 objects: the sun, the earth, and the neutron stars. Here you can see the radii of these objects, the mass as expressed as a multiple of neutron star, solar mass, and here we have the volume, okay? And now we want to look at the ratio between the volume, the density of a neutron star and the density of the Earth. This is a tremendous big number, 10 to the 14. So how much is 10 to the 14? This is the difference between a 10 euro bill and the total German income. So the total German Bruttosozialprodukt, I don't know how to say it in English, you know, but all the money which is, you know, acquired by transition in Germany. So that's the ratio, okay? This is 10 to the 14, so it's an immense number. And now you think, I mean, and now you could be puzzled. You can say, excuse me, but how can it be that you have this difference? Where does this come from? Is this exotic? Actually, this is not that exotic. This is due to the very nature of the atom we are built of. Indeed, if you think about the atoms, with all the electrons orbiting around a nucleus, you have to be reminded of the dimensions of the atom and the dimension of the nucleus. The atom has a radius typically of 10 to the minus 10 meter, while the nucleus is very, very small. It has only 10 to the minus 15 meter. To make you another example, so if an atom is as big as a football stadium, the nucleus is as big as a rice corn put in the middle of the stadium. That's the difference. So this tells you that the huge difference in density is due to the fact that actually the matter we are composed of is rather empty. Well, basically, neutron stars are much more dense. And now let's make the simple back of the envelope comparison of the density of the atom in comparison to the density of the nucleus. If we do so, we compare volumes only, we get again 10 to the 14. So mainly, this is now, here you see the reason why nuclear physics is so important for the physics of neutron stars, because basically it interests the properties of the nucleus only. Instead of having just a nucleus with a finite number of nucleons, inside the neutron stars you may have an infinitely large nucleus, right? And actually, if we look at numbers even a bit more carefully, what we see is that if we take the normal density of nuclei, which is constant for all the nuclei we know, probably inside the neutron stars, we even have factor 3 to 6 times denser matter, because these constituents, they are really packed extremely close to each other. Okay, so I hope you got a flavor for how dense is dense and where this comes from in this simple example. And now, let's come to the recipe. So, we want to cook the recipe, right? And normally when you cook a recipe, first of all, you have to go to the supermarket to buy ingredients. So we have, in the case of a neutron star, to know what is inside the neutron star. And if you just look at the name, it is intuitive to think that you have only neutrons. And this is also what many people think, that you just have neutrons inside neutron stars. If we look a little bit in detail to the neutrons, we see that it's not a point-like particle, but it's composed of quark. And here you see a representation of a neutron, which is composed by 2 green balls, which here represent 2 down quarks, and 1 red ball, which is an up quark, okay? So this could be, possibly, question mark, but there is another hypothesis, that the slightly heavier brother of a neutron, which is the hyperon, which has the difference to having a strange quark in its content, so you have a different quark inside, might also be a viable possibility, right? It's not the only possibility, but it's a possibility that can be investigated. And I do that in my daily life. I have focused in the same way. Basically, you can have a star which does not contain only neutrons, but even with a certain fraction, some hyperons, right? And now, this is exactly what we want to know, whether the constituents are only neutrons or whether the constituents can be seen as a mixture of different particles with different quark content, okay? So now, in order to proceed and to see how we want to cook this recipe, how it looks like, I have to introduce another concept that is typical in physics, which is the equation of state. What is the equation of state? This is simply the answer of the system to external pressure. We can, for example, take a pillow and try to compress it. And this will be easy. So, in this case, we can compress the system. The system does not exercise too much resistance. Then we speak about a soft equation of state. If you try the same with a box, a wooden box, you will encounter more resistance, right? It's much more difficult to compress with your hand, for example, a wooden box. Then we say it's a stiff equation of state. So, and basically, the stiff equation of state means that if you try to increase the density of the system will rebel, meaning it will exercise a strong external pressure, so from the inside to the outside, to resist your compression, okay? So you can imagine that this concept can also be applied to the neutron stars. And this is the key of combining nuclear physics to the physics of neutron stars. Indeed, we will now see how to represent in the language of physics, so in the language of a function, an equation of state. We need a diagram. So again, on the x-axis, you have the density. So if you want, this is nothing else than a scale of how much you compress. If you compress a lot, you have large density. And on the y-axis, you have the pressure of the system, meaning the opposition, if you want, of the system. And what you see that this green line goes up. The larger is the density, the larger is the pressure. Okay? This is simply true for all systems in this world. Doesn't matter if soft or stiff, it always goes up. And now, what's here the magic? The magic is that this line, okay, correspond one-to-one to, with a little bit of math, to a line on the mass versus radius diagram. Meaning, imagine we would know the equation of state of neutron star. Then we would be able to trace a line, and only one line to rule them all, that tell us, for a given mass, which is the radius, it tells us everything about the neutron stars. So this is a little bit more my job, so I try to help theoreticians establishing this equation of state, okay? I don't really do it by myself, but we try to help them to find out this line, because if you have this line, we immediately know everything about the characteristic, okay? Very good. So, meaning that this range here is mapped univocally to this range goes here, and this range of equation of state goes here to the maximal mass that a neutron star can have. Okay, so now, what is our job? So what is this recipe? The recipe is the line, basically. So we nuclear physicists, we want to complete the diagram where astronomers put measurements of mass and radii with a line, okay? And clearly, if the astronomer would be better than, or better off, or more, let's say, advanced, they would be able to give us little points for each neutron star. So they probably would be able even to give us this line. But this is not like that. So this is not like that. That's why we need to work together from both sides. Okay, so basically now you know what is the recipe of neutron stars. This is basically one line. We are looking for a single green line. And now I have to explain you how to do this, because this is now where things becomes complicated for us, because we have to understand how to do it. Okay, I told you that one possibility is that instead of having only neutrons, you can have hyperons. So those heavier brothers of neutrons which contain a strange quark. So here you see, if you put them on a scale, the hyperon is slightly chubbier. So, and now the question is, why is this hypothesis a valuable one? Why people bother, right? Normally, nature is greedy, as you all know. Try to save money. So why should a neutron star accommodate an heavier particle if it can go home with a light one? So in order to explain that, we have to think about the gravitational pressure. Each of you know that gravity acts. Right? Without gravity, the neutron star would not exist. Then also try to compress, okay? Try to compress. And if you have this big gravitational pressure, the system experiences not only an increase of density, but actually the energy of the neutrons increases, okay? If you are acquainted with the concept of Fermi energy, what happens is that the Fermi energy of a neutron goes up. So, but in few words, the system becomes very expensive. It's like a car that you need to repair all the time, where you have to put a lot of money. At some point, what you do, you change it, right? Because on the long run, it is less expensive. And this is exactly what the system does. It resorts to new degree of freedom, because by putting in hyperons, the energy goes down. The pressure is released. And that's why it is energetically favorable to have different particles, because basically the system will decrease the energy, okay? So this is a natural process. This must happen at some point, because nature is greedy, wants to save energy. And this is why it's this hyperon idea, although they are more massive, since they are different from neutrons, they can occur. Okay, but then what is actually the problem? So why should we now put effort in understanding this equation of state, or finding this recipe, if it is so clear? Because unfortunately, there is a problem. This problem is called Hyperon star puzzle. And indeed, let's go back to our equation of state. Okay? So we have learned now what an equation of state is, pressure against density. And here we have the original equation of state in case you have only neutron. And we can call it stiff because it goes up very quickly, so it's stiff. And with some math, we have the one-to-one correspondence. You have a line on the mass versus radius. Okay? Good. What happens if the system introduces Hyperon, right? Unfortunately, or fortunately, the equation of state becomes softer, right? Because how I have, what do I do to save energy, right? I diminish the pressure automatically. So this line will go down. And now the question is, what happened on that plot, right? And there we have a little bit of a problem. Because in the moment where on the left plot, so when the recipe gets softer, more creamy, unfortunately also in the case of mass versus radius, the curve will change. And all of a sudden, the mass, the maximal mass that you can reach with this curve will be smaller. And now we have a problem because we have measured two solar masses, and now this line doesn't cross the measurement, and this line must be unique, we said. We want one line to cross all the measurement because we want one recipe. This is the Hyperon star puzzle. Hyperon should be produced. It is a available hypothesis, but if you produce them, then all of a sudden, you are not able anymore to explain the very massive stars. And then you have a problem. Your system doesn't match. OK. So now, obviously, things are not so easy as I showed. We don't have only one Hyperon, which we indicate with the Greek letter lambda, capital lambda. But we have actually several of them. So they are all called with cozy Greek symbol name, lambda, sigma, and xi. And all three of them, they have different properties, and all three of them could occur. So you see, you have a very colorful ensemble. And now, finally, after I am talking now already for a while, I want also to show our little contribution as experimentalists, right? Where do we come in? The equation of state, so this line, green line, depends on the interactions, okay? It depends on the nucleon-nucleon, but also on the Hyperon-nucleon interaction. Meaning, if the interactions among this colorful ensemble would be all attractive. Imagine you have many people who all attract each other, they will tend to cluster, right? If you have only attractive interactions, you have less pressure to the outside, so you have a softer equation of state. It's like the pillow you can compress. If you have, although partially repulsive interactions, then people will not be so happy to stick together. They will try to keep the distance, right? Same thing in the neutron stars. If you try to compress, the system will exercise pressure to the outside, right? So we'll have a stiffer equation of state. So then you understand that in order to draw the line, it's not only enough to have the constituents. So in our book of recipe, we don't only need the ingredients, the Hyperons and the neutron. We also need to know the interactions. And this is what we do in many different experiments in the world. And we are also involved within the ALICE collaboration to do that at the LHC. And now I am going to tell you what we do to help this business. And in principle, if we have all the constituents, we have all interaction, we can then draw the final equation of state and then go to the mass and radius and tell the people, hey, the recipe is this one. And then we know everything we want to know about these wonderful objects. Now, what is left is to show one possibility of looking at this interaction. Obviously, it is my favorite one because it's the one I do from dusk till dawn. And now I want to bring you on a journey in a very fascinating place. This is the LHC. So I'm sure you saw already this movie, potentially, of how particles, two protons or two heavy ions, can be accelerated up to 13 tera electron volt. You have injectors, and then you have a Large Hadron Collider with a circumference of 27 kilometers. And we go now down 100 meters below the Earth, and we go inside the tube where particles are accelerating, running against each other along this circumference. Here you see the proton with its 3 quarks, which are colored differently. And then when you have the energy that you want, patapam, you collide, right? You collide. And here you see, this is unfortunately not the Alice detector, but there is a secondary one at the LHC. But, the thing now that you have to understand is that when you collide two particles at a very high energy, you can create many new particles. That's the trick. Among these many particles you create also hyperons. So you can now go and pick them up and look at the interactions, so that then this helps you to cook the recipe. Okay, so basically, you see this is now a schematic view of our two interactions where many particles are produced. Indeed, energy of the accelerating protons can be partially transformed into new mass. This is, let's say, Cesi's fundament on the equation, master equations that you all know. Energy is is equal is equal mass times the square, meaning energy is mass, right? If you have a lot of energy, you can distribute it in producing many particles. And that's simply the trick. In each of the collisions at LHC, when you collide two protons, we have about 30 new particles in each collision. And then, for example, we can look at protons and substitute instead of looking at neutrons, because they are easier to see. So we treat them same, okay? So instead of looking at neutrons hyperon interaction, we look at protons hyperon interaction, simply because it is simpler for us, okay? But you have to believe me that this is a good help to understand all this story. And protons are cool because you produce many of them and they are stable. So they go through your detector. Hyperons, they are more complicated because they decay. But we can detect the decay products, so the so-called daughters. And by looking at the property of a daughter, we can trace back the mother, which is the hyperon. So in few words, we can measure very accurately the trajectory, the velocity, and the mass of each particle that is produced. And how fast we do that? We do that with 1,000 photos, 1,000 events per second, which is quite a velocity. Okay, and I want to show you our beautiful Alice detector, actually a part of it, just to show you that it's not really science fiction, but we can really see each particle. Here you see my favorite detector in Alice, the time projection chamber. This is a three-dimensional camera that allows you, after the collision, to really trace particle by particle, reconstructing the trajectory. And then with the help of other detectors, we determine the velocity and the mass. And here you can see this detector allows us to project a trajectory on a XY plane. You see now on the rotation really the beautiful curvature of these particles. Why are particles curved? Because there is a magnetic field that will curve charged particle. This helps us a lot in determining their velocity, their momentum. Then you have other detectors that allow us to determine the velocity. And basically, the take-home message from these slides is that we know exactly the properties of the momentum and the mass of all particles, okay? Now, we have to find a way to study the interaction, right? Because the theoretician needs the interaction from us. So, how do we do that? We had an idea at some point. And this idea came from thinking about a party. You go to a party, you are a young girl, and you meet a boy. And then what you do, you talk during the party. At some point, it's time to go home. And then you can either go together to some other bars, right? So, and if you go together, you will speak to each other. So, meaning that your momenta, which is nothing else than velocity times mass, will stay parallel because you talk to each other and you walk, right? And you have time to talk. Same thing happens to particles. If you produce them with momenta which are parallels, they have the possibility of talking, right? And then if they talk, they can undergo attractive interaction, and if the interaction is attractive, you come closer, right? If the interaction is repulsive, you will at some point go separate ways. That's the idea. And this is what we do at the LHC. We basically look at the situation whether the momenta, right, this indicates the direction of the movement of a particle, whether the two directions come closer to each other along the way from the production to the detector, or if they go apart. Easy as that. Mathematically, you can express this basically with a formula. And this formula helps you to understand how much attraction or how much repulsion you have. This is basically the way we measure the interaction. This is the only plot I show you. Not really true. I show also other two. But what do you see here? Now we have to concentrate a bit. If we measure, for example, we want to study a lambda-proton interaction, right? Lambda is the hyperon, the lightest of the hyperons. I can measure the relative difference of the two momenta, so the relative difference of this momentum, which is mass times velocity, and then I can put it on a x-axis, right? This is basically here, this k star is the relative momentum. If k star is very small, it means that the particles are parallel to each other, okay? If k star is very large, it means that they diverge, right? And now you can measure a so-called correlation function. This correlation function is 1 if you have no interaction, okay? Then you will measure something which is flat. If a correlation function is larger than 1, it means that the particle experiences an attractive interaction. And here you can immediately see that our measurement, which actually were published today on PLB, so this is a good day to show you this, show you that mostly the lambda proton is an attractive interaction, right? And if you would have a repulsive interaction, you would see something between 0 and 1, okay? Obviously, in order to quantify the strength of the interaction, you need a formula, you need theory. That's why you don't have only the data points, but you have also these lines. These lines are the interpretation of our data, right? We measure something, but we always need the theory people to tell us how attractive is this interaction. And they can tell us because they can predict the observable, and then they can tell us how attractive is this interaction case. Okay, actually we were not lazy during COVID. We did a lot of measurement within the ALICE collaboration. And as I told you, it's not enough to measure just lambda proton because you have also other possibility. You have many interactions that are relevant and needs to be looked at. And this is just an ensemble of several panels where you can see in each panel a different analysis which taught us how all this interaction works. And basically now we are not done because we have in some cases to still measure combination, and in some cases you see we have very large uncertainties. And this is bad because then theory doesn't know. You know, you have several curves and you cannot distinguish among them. You want to have for all these interactions the situation we have here for P lambda with very, very, very small error because then we can really help the theoretician. But still, the ground is broken. Alice demonstrated that the great experiment at LHC can do that. And now it's just a matter of measuring new data. And we are about to start a new experimental campaign in 1 month, which will give us 500 times more statistics. But before we go home, I want to give you now an example of what we can do with this measurement, because we already did some full-fledged calculation to go back to the neutron star. Just to give you an example. Okay, let's remind ourselves what is the path from us to the neutron star. We measure the correlation tells us about the interaction. Then I can use now the lines here, the theory lines, because I know they are solid, they have been confirmed by the data, to produce an equation of state. And if I have an equation of state, I have directly also a mass P. So we did that, we did at least with everything we have at the moment. And this is, let's say, a different representation of the equation of state. It's identical to, in the content to what I showed you before, but instead of having pressure as a function of density, here you see explicitly that you have neutrons, which at the beginning are 100%, that at some point, that at certain density disappears to leave place to this Greek letter, the hyperons. Okay, this tells you when that really manifests to you that hyperon really appears, right? And now if you do the transformation, you get this line. But it seems that with the interaction that we have measured so far, maybe hyperons are not completely disfavored. This is only an example because the theory people in the audience will be completely nervous by seeing a line, because obviously when you publish a paper, you need a band, you need uncertainties. But this is just to show you that we can cook, basically. But we don't know yet whether this is really the true, and especially we have to put uncertainty on this. There is one thing which is very close to my heart, and I want to tell you. One thing that it's important to know is actually two-body forces are not enough. Because although the strong force which governs the physics of neutron star is a short-range force, meaning is the first neighbor force. The neutron cares only about what it is really surrounding him. Still, if you are in a very compact environment, probably also so-called three-body forces are important. So, and this is something which, when you have an hyperon involved and two nucleons, is actually not known at all. So this is our next challenge. Next time I come to Prague, maybe I can tell you something about that. I thank you very much for your attention. I am done.